So last time we finished with the girth of a graph, and we are going to continue now with a bunch of other measures that I want to show you. This won't be the last of the lectures about this. Think the next lecture will include some more measures, and then we'll start working on actual real examples to look at. Now, the first thing that I want to look at is what is called the density. And to talk about density, we first have to remember what is a complete graph. So this is the sort of formal definition that we saw. And just in passing, in this lecture, we'll come back to a bunch of definitions we've already seen, but we will look at them in the context of actual using them to characterize graph properties. Okay. So if you recall, we looked at completeness and we said that a graph is complete if we take it from a general point of view using this definition. But what's really important in a sense is the second part of the definition. One graph is complete if and only if an arc is not present, then the reverse arc is present. This essentially says that all arcs have to be there. And if you're thinking about an undirected graph, then this really implies that every vertex is connected to every other vertex. Now, if you think about a simple graph, and this definition that this characterization that I just gave in terms of every vertex is connected to every other vertex, well, think about a graph, for instance, that would represent everybody in the world. And connectivity would be, do you have access to information about somebody else? Well, if that graph were complete, then you would have access to the information about everybody else in the world directly. So in a way, a complete graph explains, sort of illustrates the capacity for that graph to propagate information very quickly, immediately, essentially, from every vertex to every other vertex. And what we call density is what I'll get to in a second. Density is then how far away from this ideal situation you are. So if I have, let's start with an undirected graph. So if I have an undirected graph, X with a set of edges E, and it's of order n, then we have seen, and I think one of the assignments, we've seen that such a graph has, in the completely connected case, n times n minus 1 over 2 edges. Okay, because remember how this works. If I am an edge, I'm a vertex. If I am connected to all the other vertices, then I'm connected to n. If a graph has order n, so there's n vertices, then if I'm connected to all the other vertices, I'm connected to n minus 1 of them. And because there are n vertices, each of these n vertices is connected to n minus 1. So they're all connected to n minus, the total number of connections is n times n minus 1. But each vertex is connected to another vertex, and that vertex is connected to the original vertex. And so each edge is counted twice. So when I want to count the number of edges, I have to divide that number by 2, hence that quantity here. When I look at directed graphs, then I don't need to divide by 2 because I'm complete if I'm connected to, if X is connected to Y and Y is connected back to X. So that tells me that the maximum number of arcs in a directed graph without loops, of course, is n times n minus 1. If I allowed one loop on each arc, I would have n times n minus 1. But let's forget about loops for now. Okay? And now, if I have a graph that is not complete, and it's an undirected graph, then if I say, well, P is the number of edges, that number of edges that I have, if I divide it by the total number of edges, that's the fraction of the edges that are present. And likewise, so that's that first formula that you have here at the bottom here. And likewise, if my graph is directed, then what I have is that I have P, if I have P arcs, then P over n times n minus 1 is the density. So, and just in passing, so oftentimes you will see that in math, we tend to speak about density this way. In social sciences, this might be expressed as a percentage of the arcs or edges that are present rather than a fraction. But it doesn't make any difference. If you see a number bigger than 1, it's probably a percentage. Well, it would have to be. Otherwise, try to see what's happening. So let me show you an example, and we're going to keep on using this graph that we saw a few times in the past. I'll use it as my recurrent thing that I can actually show you things about. And so this graph here, let me compute the density. So this is the graph of order 6. It's a directed graph, and I've removed the loops. Therefore, what I should have is a maximum of 6 times 5, so 30 arcs. If a graph were fully connected, so if it were complete, I would have 30 arcs. I count the arcs, and I find that there are 8. So this means that the density is 0.2 something. Okay, so 26% of the arcs are present. And that's important when you're looking at a graph, because it tells you like how likely it is that a link exists. If you have a very densely connected graph, it means most of the arcs are present. If a graph is not that connected, then there's way fewer arcs or edges, and therefore the graph is much less connected. And in particular, that's interesting if you find some vertices that are very connected to a few others, because they would be dissimilar to a large extent from the regular vertices. Oh yeah, I was adjusting my camera. I hate it when people talk to me on Zoom and they have half of their faces missing. It wasn't my entire face by far, but it still doesn't match my way of filming things. One of our colleagues appears as the top of the head. I find that infuriating, so I'm trying to fix this. Okay, so density is this very important quantity that allows us to see how connected a graph is. And another very important quantity that I'll talk about here is connectedness. And so we've seen that already. We've seen connectedness, and in the case of a directed graph, we've talked about quasi or strong connectedness. And connectedness is equally important. Well, I mean, it's actually very important. I shouldn't say it's equally important to density. It's probably more often used because, okay, density gives you a notion of how well connected things are. Connectedness gives you an idea of how easy it is to propagate information. Okay, so connected density, if a graph is very dense, it means most vertices are connected directly. But if a graph is not very dense, then you might become interested in knowing, well, can information flowing along this graph actually make it from one place in the graph to another? And that's why connectedness is so important. Okay. Now, I'll come back to, as I said, this will happen a few times, the definition of a connected graph. So a connected graph, here we're thinking mostly in terms of undirected when we give that definition. Okay. I mean, it works the same way for a directed graph. That definition still holds, but it's not as interesting in the case of a directed graph. So a connected graph is a graph that contains a chain from between every single pair of vertices. And that chain, remember the difference between a chain and a path, is that the chain doesn't necessarily, if you're looking at a directed graph, the direction in which you follow the vertices, the edges, so arcs, is not important. So a chain, you could follow an arc this way and an arc that way and go like this, and you would still be on a chain, but you would not be on a path because the path has a direction. Okay. And recall that we defined connected components using this equivalence relation, which is simply x is equal, so two vertices are either the same or they're not the same, but there is a chain in the graph that allows me to go from one to the other. And we've seen already that this defines an equivalence relation, and that means that we can think about vertices that are equivalent in terms of that relationship as representative of a class of equivalence. Okay, and so the classes of equivalence of this relationship, they give you a graph that is partitioned into a certain number of subgraphs, and in each of these subgraphs, all the vertices have the property that they follow that relation. Okay? And those subgraphs are called the connected components. I'll remind you, because this is something that is used from time to time when you're looking at graphs, that we defined an articulation set as a set of vertices, which is such that if you remove them, the graph is no longer connected. Okay. We'll come back to that when we look at examples. And as we progress, as you can see here, I will from time to time highlight what the iGraph function is that gives you such a property. And here, for example, for articulation sets, you look for the function in iGraph is articulation points of G. And I'll make it clear that this works only on undirected graphs, in the sense that if you use it on a directed graph, it will assume the graph is undirected, and just use it as an undirected graph. Okay. Now, a strongly connected graph. So when you see the word strongly or weakly, as we'll see later, you have to think that here we're really thinking in terms of graphs that have an orientation. They're directed. Okay. So suppose I have a connected graph. Okay. So I'm starting with a graph that is connected. Then a path of length 0 is a sequence that contains a single vertex, and then afterwards I can, the same way as I did for undirected graphs, I can define an equivalence relation. That is that there is a path from x to y for any pair of vertices. There's a path from x to y and a path from y to x. This again defines an equivalence relation, and the strong components of a graph are the equivalence classes of the graph under this equivalence relation. Okay. So this is what we call the strongly connected components, or strong components of the graph. And the graph is strongly connected altogether if it is a single strongly connected component. Okay, so the number of strongly connected components in the graph is going to indicate whether the graph is strongly connected or not. We also saw this definition, which was that a graph is minimally connected if it is strongly connected, but that whenever you remove an arc, you destroy that property of strong connectedness. So you have a graph that's strongly connected, remove an arc in there, and the graph loses the property of strong connectedness. Then you're minimally connected. And I'll just remind you, because this is something we'll see later again when we're looking at graphs, that we could contract the graph in terms of the strong components that are there and replace each strong component by a single vertex. And that is now a graph that is similar to the one we had before, except that we've reduced the information. Now, we also saw quasi-strong connectedness, and that definition was that we don't quite have connectedness, but we have possibility to access. If I take any pair of vertices, I can find a third vertex that has a path from that vertex into both of the vertices that we're considering initially. So if we have strong connectedness, we have quasi-strong connectedness, but of course the converse is not true. It's easy to think of examples. Well, just take a graph. I mean, there's a few. Okay, so the annoyance, by the way, I will be back on Lightboard, I hope, for the next lecture. But that's actually one of the annoying things. I'd like to be able to scribble away, and I don't think I can do this. I could probably, well, no, I won't do it for now. Okay. I might be able to put it in a little thing there. I'll check. Okay, and so that's just a quick reminder on quasi-strong connectedness. What do I want to look at? This is something we haven't seen so far, but it's really similar to strong connectedness. It's actually, weak connectedness is essentially connectedness, but when you're thinking about directed graphs, specifically directed graphs. So if you think about a graph X and U, so I'm thinking about a graph with an orientation, okay, a directed graph. That graph is weakly connected if the graph that I get by forgetting that there is an orientation, so there is a direction in my arcs, is actually connected. So I've put an example there. This is a graph. So if you look at that graph at the top, this is a graph that is not strongly connected, okay? Because whenever I make it past x2, x1 and x2 form a strong component. But whenever I make it past x2, so if I'm in 3, 4, 5, or 6, I cannot make it back into x2 or x1. And therefore the graph is not strongly connected. But now let me take the equivalent graph in which I've forgotten the direction of the arrows, and where I just, if I have two arrows, an arrow in each direction, I just put an edge, whatever. I'm not doing a multi-graph, I'm just doing a graph in which whenever there is at least one arrow, I have an edge. So this is the equivalent undirected graph, and that one is connected because I can go between any two pair of vertices without any problem. What that tells me is that the graph above is weakly connected, but not strongly connected. And exactly the same way as we had for strong components, we can define weak components. And these weak components were defined exactly using the same equivalence relation as we had used to create components in general. Okay, but here I'm really thinking about a graph that is directed. So I define this equivalence relation by saying that either the vertices are the same or they're not the same, and there is a chain. So that means that the orientation of vertices is not important, of arcs is not important. So there's a chain from x to y. And that, again, defines an equivalence relation. And if we use this equivalence relation to define sets of subsets of the graph, then we get the weakly connected components. And a graph is weakly connected if there's a single weak component. Okay, so this is exactly the same as before, except that we have this notion of weak or strong connectedness. I stress this is exactly the same thing as considering the connectedness of the graph that you obtain when you ignore the direction of arrows. And in iGraph, because as I said, as a measure of the importance of the capacity, not the importance, of the capacity of a graph to propagate information, connectedness is very important. And you can see this because you see all the functions that iGraph has to allow you to consider these properties. So one is connected. So that is going to tell you whether the graph is weakly or strongly connected. So in all of those functions, you're going to have to say whether you want weak or strong connectedness. And it's going to give you an answer depending. And if you have an undirected graph that you use, then it's going to use weak connectedness because, as I said, this is equivalent to connectedness. But in the case of a directed graph, you're going to have very different results whether you consider weak or strong connectedness. Components just find the maximal weakly or strongly connected components of a graph. Maximal means that you can't grow them anymore. Okay, they're the largest that you can find because, of course, if you have a strong component or a weak component consisting of a certain number of vertices, you can very easily find a subset of these vertices, which is still a strong component. Okay, so what you want to do is you want to find the largest possible sets every time. So components is going to give you this. Count components does the same thing as components, except that the only thing it does is tell you how many such components there are. And again, weak or strong depending on the options that you give. Component distribution gives you a distribution of sizes. It makes a histogram, and I will give you a bunch of examples in Jupyter Notebook later. Okay, but so component distribution is going to give you a histogram that shows you how many components there are of each of the different sizes of components that you have in the graph. Okay. Decompose actually takes each strong component or weak component and puts them apart. So this would be a way to say, okay, I've got a bunch of components. I want to work on each of these individual components, and it's just going to give you a bunch of graphs, each of which is a strong component or weak component, etc. And subcomponent is actually quite interesting. It's the beginning of the work on a component, and it actually matches a little bit. I mean, it could use Dijkstra's algorithm to compute this, because what it does is it finds the vertices that are reachable from a certain vertex, or the vertices which can reach a certain vertex. Okay, so if I'm somewhere in the graph, it will tell me how I can project forward what are the possible vertices that I can reach. And again, think of this in terms of diffusion of information or diffusion of something. If you have access to very few vertices, then you're not going to be propagating your information too much. Whereas if you have access to a lot of vertices, your information is going to spread forward in the graph in a good way. Good or bad, but it's going to be able to do it. Now, another notion that is important is cliques. So we will probably see more about cliques, but let me explain cliques a little bit. So let's start with what happens for a clique in an undirected graph. So take a simple undirected graph, simple in the sense that it's a one graph, okay, and it has no loops. A clique is going to be a subgraph of this graph. So if G is the graph, G prime would be that subgraph, such that all the vertices in the clique are adjacent. So that means there's an edge between them. Okay, so a clique is a set of vertices and the corresponding edges, such that if you want, such that the subset, the subgraph that is in the clique is connected. Okay, so I have access to all the other vertices in there. And the highest type of clique is if I have a simple complete graph with of order n, then this is what we call an n clique, and it's typically denoted kn. So for example, if you take a star with 5 vertices, then each vertex is connected to all the others, so that's where you get your nice star. This is k5, and it's the complete graph of on 5 vertices. Now, in a directed graph, things are a tad more complicated because you want the vertices to be mutually adjacent. So if I take any 2 vertices in my graph, then they are all linked by arrows in both directions, arcs in both directions. Okay. And finally, we define a maximal clique as a clique that cannot be extended by adding another adjacent vertex. So this is very similar to what I was saying before in terms of strong components when I said one of the function looks for the maximal strong components. Because if you have a clique, well, it is possible that you haven't grown it enough and that you can find a vertex that's adjacent and that's still in the clique. But typically what you're looking for, of course, are the maximal cliques. So you are looking for something which encompasses all the vertices that would satisfy the property. Okay. So let me show you an example of cliques with our friendly neighborhood graph. So at the top, I'm looking at the directed version. So remember that in the directed version, the idea is that the vertices and the subgraph is strongly connected sorry, it's not only strongly connected, it is complete. So the only clique that we can find in this graph is x1 and x2, because those 2 vertices are linked by an arc, so they are both mutually linked. In a non-directed case, the undirected case, the clique is different actually. So if you take that thing that I've highlighted in red here, that's a clique, and that's actually the only clique in this graph, because here in this graph, all vertices are linked to every other vertex in the same way. So that one is linked to 2, that one is linked to 2. I mean, you could think also of both those pairs. Okay, I'm not being, I did not give all the vertices, all the cliques, because that is also a clique in a sense, and that is a clique, and that is a clique. But here we'll focus on this is complete in this sense. Okay, so this is really to highlight that the maximal cliques in both of those graphs, which are the same graphs except that I've removed direction in the second case, they don't necessarily match. And that is a very common problem, so to speak, between graphs that are oriented or directed, directed, and graphs that are not directed or non-oriented, okay, because they don't have quite the same property. And this is just a remark in passing. People who do graph theory a lot of times in the mathematical world tend to focus on the non-directed case. There is way less work on the directed case than there is in the non-directed case. But both are interesting, and in terms of applications, most of the graphs we consider are actually directed. So that's why it's important to be able to go from one to the other, but bearing in mind the fact that they don't necessarily have the same properties. Okay. And in iGraph, there's a few functions to look at cliques. So cliques just find all the complete subgraphs in the input graph. And this is exactly what I was saying here, because this would work under specifications. Typically, we don't like to consider x3, x6 here, for example, as a clique, because otherwise it means whenever I have two pairs of vertices, okay, if they're linked, I have a clique. But typically, so that function here, it assumes that there is a minimum size and a maximum size that you're looking for. Maximum, typically you don't specify, but minimum, oftentimes you will say 3. And that means it will find a clique of size of minimum 3. Largest cliques finds all the largest cliques in the graph you're considering. Maximal cliques finds all the maximal cliques, and this is a remark that I left, that's in the function description. Largest cliques are always maximal, but a maximal clique is not necessarily the largest. Okay, because remember the definition of maximal is that I cannot grow it any further. But it's not necessarily the largest clique. It simply means that locally, where you're looking in the graph, you're not finding anything that is larger. Count maximal cliques, count the maximal number of cliques, and clique number returns the size of the largest clique. And I realize that I am really going to be short for this lecture, so well, that is not so bad, because this means I will then go to CZG. Hopefully it works. By the way, I know there's been a few issues. I hope this is fixed soon. So I will do a few examples with all that we're seeing here. Now, the last measure of a graph that I want to look at today has to deal with degree. So I'll remind you how we define the degree of a vertex. So by the way, what we looked at before, these were graph properties. Okay. Degree distribution is both a property of a vertex, but when you're looking at distribution of the degrees in a graph, you get some sense of how the graph is organized. And we'll do quite a bunch of this later. No, but first I'll remind you, so the way we think about degree is we start by thinking about arcs incident to a vertex. If I have, and this is to define in the directed case, the undirected case is easier. If I have a vertex that has initial endpoint, that is the initial endpoint of an arc, we say that that arc is incident out. It moves out of the vertex. And if I count this, and I also count the number of loops attached to a vertex, then I have the outer degree. I've used the term outer dummy degree, but most of the times, remember I said this comes out of an old book, which I think is very good, but some of the vocabulary has changed, and most of the time now you will just see it called outer degree, not outer dummy degree. But I mean, it's a dummy degree because it's half of the component of a degree, the other half being the inner degree, but people have forgotten the dummy now. So the number of arcs going out of a vertex is the out degree, and the number of arcs incident into the vertex, so finishing with the arrow tip on the vertex, is the inner degree or the inner dummy degree. And the degree of a vertex, in a case of a directed graph, I would take as the sum of the two, but we often don't do that. Okay, I'll make it clear. So when you're dealing with degrees in a directed graph, most of the time what you're doing is you're saying, well, I'm looking at the out degree or I'm looking at the in degree. You don't count the degree as the sum of the two. If you have a non-directed graph, an undirected graph, then the degree is simply the number of edges that touch the vertex. Or if you want to see it in another way, which we will do soon, the degree in an undirected graph is the number of neighbors, direct neighbors, that a given vertex has. And this is going to be important. That's why degrees are so important in the study of graphs, because they say something about how you as a vertex, so if I consider myself a vertex, how you as a vertex connect to the rest of the world. Okay. So here I've taken our friend the graph, and I've replaced the vertex names x1 to x6 by their actual degree. So in the undirected graph, as I said, it's very simple. You just count how many edges finish at a given vertex. So the degree is 3 for those that are connected to 3 of the vertices, and 2 for those that are connected to 2 of the vertices. Here, I mean, okay. In a directed graph, it's a little bit more complicated, and I've taken 2 cases here. I've taken one where I've looked at a proper digraph without loop, and the second one at the bottom is a digraph with loops. So you can see I've indicated here, I've removed again the name of the vertices, but you can see that what I'm showing you is the out degree, so that's the number of arrows going out, and the in degree, the number of arrows going in. So that in degree is 2, and that out degree is 1. Here, out degree is 3, 1, 2, 3 here, and the in degree is 1, and so on and so forth. So you have these examples, and remember that when we are looking at, this was part of a definition, which I skipped over. Where is this? Yes. The number of arcs incident out of X plus the number of loops attached to X is denoted dg plus. Okay. So here I've added a loop. And if you think of this loop, well, it contributes to the out degree because it's going out, but it also contributes to the in degree because it's coming in. And so where I had d plus equals 3 here, I have d plus equals 4. And when I had d minus equals 1, I have d minus equals 2. Okay. So this is a very simple graph. Of course, where it's going to be interesting is when you have a much larger graph. And so let me explain a little bit what you would consider as degree? What type of measures you would look at when you're considering degrees? So first of all, it's always good to think about what the measures that you're using, what do they represent. And when we think of degree, we often think about popularity in a sense and outward goingness. So I'll explain this in just a little while, okay? Maybe I should do that right now. So think of yourself as, think of a social network, for instance, or you're on Twitter. I don't know, I'm not. You're on Facebook or something like this, and you can follow people and you can be followed by people. The number of people that you follow is in a sense an indication of how outward going you are. Okay? You want to know more people, you want to make more friends, or etc. The other way around, the number of people that follow you is how popular you are. Okay, and so for example, you take like influencers or well-known stars or whatever, they'll have an Instagram account or a Twitter account and something like this, and they'll say, I have 1 million followers or I have 10 million followers. That relationship is not symmetric. Okay, a lot of people are following these people, but they are not following you back. So the fact that they receive a lot, their in degree is very high, means that they're very popular. If on the other hand, your Twitter account or your whatever account you're following 50,000 people, you really want to know people. And that indicates that you're outgoing, okay? So that's why degrees are so important. And this works in another context, and I'll show you in a second. So the terminology essentially the notation has evolved to the one that I'm writing here. You very, very often will see the letter K used as the degree. Often it will be written just K, but thinking about K as a vector. Okay, K equals K sub 1 to K sub n, etc. Or we'll write K of I to say the degree of vertex I. You'll see written K minus and K plus for in and out degree in the directed graph case. Okay, but the most important one is typically like this, K of I, or just K, but thinking K sub 1, 2, 3, and so on. So when you look at a graph, it's easy to get the degrees, as I was saying. So we can look at the inner or out degrees, or we can look at the degree in the case of an undirected graph. A bunch of things that you're going to see looked at is, well, the minimum and the maximum degree. Okay, because that's going to give you a sense of how much variation there is, essentially. Where does the degree vary? If I have a graph that's quite large, the maximum degree, so if I have a graph of order n, and suppose I'm thinking about Twitter, I don't know how many million, hundreds of millions of users there are, they could technically each follow each other. But okay, that never happens. But what's the maximum degree? So what's the highest number of connections that someone has? And sometimes we can look at them from the non-oriented case, but non-directed case, okay, and that would be the minimum and maximum degree. But oftentimes you'll see it looked at in terms of minimum and maximum in and out degree. And I'll give you an example later on. I mean, I'll show it to you here, but we'll play with it a little bit, where we consider the global air transportation network. Okay, and if you think about this, well, I have Airports are nice in the sense that, well, airports and air transport is nice because it's a very easy to quantify graph. You can't leave an airplane while it's flying. So if you start here and the plane is flying to there, you're going from here to there. And so we can count people very easily when they do these things. So this is a very nice network to consider. And in that sense, if you look at airports, you can use what I was saying in terms of the measure of popularity. Your in degree as an airport is a sort of measure of how popular you are. And your out degree is how much your population wants to go to other places. It's not really, I mean, I think it's all about popularity. If you think it's not really outgoing versus ingoing, it's really more a measure of popularity. Okay, because typically, if you fly from A to B, you also fly from B to A. It's very rare that you have triangles and things like this. So essentially the degree of an airport really represents how popular that place is. And I'll show you a graph of this in a while. Another thing that you can look at is the range of degrees. So how much difference is there between the minimum degree and the maximum degree? The same way, you can look at the average degree. And I'll point out that it's often denoted this way because this is how physicists write averages, typically. I would rather put a little bar on top, but a lot of the work that's gone into considering the properties of graph comes from physics, and that's their notation, and so you'll see that a lot. So the average degree is something that is quite important. The average in and out degree, exactly the same, but keeping in mind the orientation. The variance also. I was talking before in terms of how much variation there is. So if you have a graph that is not strongly connected, or that is strongly connected but not complete, so very low density, but if you find a large variation in the degree distribution, so if some vertices have very high degree and most of the vertices have low degree, then you know that the situation is not very straightforward. There are some people that, if you think of propagation of things, there are some people that are going to be very apt at propagating to a large audience, and a lot of people that are not going to be apt to do so. And the example that I was using earlier in terms of Instagram would be a typical example of that. If you have someone who's an influencer and they have a very large following, that's why they get good money in terms of advertising, because it's expected that when they propagate, well, I mean, when they talk about a product or something like this, they reach a very large audience. But the average connectiveness in these networks is much lower. And okay, so let me show you a very simple example. This is not okay. This is not the most easy to see, but I'll propagate some some of those things later. So this is a graph that I made. Must be almost 10 years old, I think. It's the Global Air Transportation Network, and I'm showing you this because these are all the airports in the world, and the size. So if you saw better, you would also see all the connections. Okay, I've indicated, and it's very difficult to see, but the number of flights is actually showing on there, I mean, like as an indication of the size of the edges. But what's important is the size of the airports there is a measure of their degree. Okay, so the larger the dot, the highest the degree of that airport. And so what you can see here is, so the biggest airport at the time was London Heathrow, and then Paris and Frankfurt, Paris, if you consider all the airports together, because there's two, Frankfurt and then the East Coast US, New York, etc. I'll come back to that because I think that's a network on which I'll get you to work a little bit. But that's an example of a network, and that shows you that the degree is important. Okay, if you're thinking about all sorts of things. So what happens in terms of diffusion of information and so on? Well, it really depends what type of degree your airport has. For me, that is important because I'm thinking about disease propagation on a worldwide scale. And so if a disease starts out in one of those places that have a very high degree, it means that disease can go to many places very quickly. Okay. I mean, keeping in the disease world, and I'm sorry, I mean, I will take examples elsewhere, but, like being an epidemiologist, that's where most of the interesting topics I'm going to look at are going to come from. This is an example of the spread of pandemic H1N1, so it's in 2009. And it's showing you spread. I believe it's in student groups. I've put the reference here, but I think it's in student groups. I don't remember where. What's interesting here is that you see. So this is characteristic of a disease with what we call a low reproduction number, like influenza, because what you can see is that these are the propagation chains, and this is the yellow guy in the middle is the initial case in that community, and then there is an edge. Sorry, it's a directed edge because you follow down these branches. So there's an edge if, for example, that first one means the yellow person in the person represented as the yellow vertex infected that person in the blue vertex. Okay. And so what you can see here is large propagation, but there are very few people that are infected. If you look at some of those branching points on the left, for example, this person just prior to the branching point infected 3 people, but it's very rare that a lot of infection. Well, that person here infected 1, 2, 3, yeah, maybe 4. There's a few infections by a person that infected more than one person, but essentially these are nice propagation chains. That's if you compare to, this is spread of MERS in Korea. And this is like a good illustration of the fact that the network, the graph, is really important, because here you have that person in the red square or rectangle on the left that has generated all these infections that you see around. I mean, all the arrows that go out of that vertex are people that person infected. And likewise, you can see that there are other vertices that generated a lot of infection. Most vertices did not generate so much infection, but a few generated a lot. And that tells you that, like this graph and this graph, they represent the same type of thing, but they have very, very different structures. This one is, of course, in terms of disease propagation, something we don't want to see. In terms of spreading advertisement, for example, suppose this were an influencer telling its influencees that they want them to, they suggest that they buy, I don't know, such and such skincare product. That would be very good for the person paying for the advertisement. Okay, whereas this would be a very slow propagation of the information. Okay, in terms of disease propagation, this is better than this, but this is the overall idea. We will see many more examples, and I'm going to, so I think here I will stop at this point, and I will show you a little bit of R to illustrate some of those things I've just talked about in a simple case. And what we will do in future lectures, I'm going to give you a few other measures of graphs, and then what we'll do essentially probably until the end of term is go through examples of interesting little things to do with that sort of things. Ah, yes, no, before I finish, sorry, I forgot I have a last slide. I have two last slides. Other things that you can consider. These, the reason I got there is that those measures are relative to degrees in general, and those measures that I'm looking at here are more specific to a few, there's a bit more advanced considerations on degrees. So, for example, one thing that you can do is consider the average nearest neighbor degree. And the reason for doing this originally is to encode for what is called preferential attachment. It's the popular people in high school that tend to have a lot of friends and that people want to be friends with because they have so many friends. They must be popular. So this is preferential attachment. And so this measure here is very important in a variety of applications in graph theory. It's called a KNN, K nearest neighbors. So it looks at, here it's the average, but we also look at just the distribution of these quantities. So if I want to compute the average of a K nearest neighbor, I look at, and what this is indicating here is the neighborhood of vertex I. By neighborhood of vertex I, we mean all the vertices that are adjacent to the vertex if we're non-directed. If we are directed, we have to decide whether we are outward going or inward going. As always, things are a bit more complicated in the directed case, but they're important. They work the same way. So what you're saying is you're dividing the total number of neighbors that your neighbors have. Okay, and you're dividing this by how many neighbors you yourself have. And you can compute that with the adjacency matrix. It's actually much easier to have. Once you have the adjacency matrix, you can compute the KNN just by taking this. Okay, this is a sum on the row entries in the matrix. There's a very used, probably even more, it depends on the domain, but there's another thing that is used, which is called the excess degree. It's very much like the nearest neighbor degree, except that it takes out the arc or edge that makes the connection. Okay, if you think about it, go back to this graph, for instance. If you look at this graph, that big red in the left-hand side, and that red here, I hope you can see my mouse. I'll have to check, but okay, the two largest red, just in case, the two largest red vertices. This person infected this person. But if you're thinking about the excess degree, well, you're saying, well, because that link is here, but that is the infecting link, what's important is how many people that person in the smaller red rectangle actually did infect. Because it doesn't really matter that they got infected by someone else. It's where they propagated to. Okay, so that's what's called the excess degree. Instead of looking at the entire degree of this thing, you'd be looking at the out degree here. Okay. And one thing that we are going to do is we are going to look at these quantities, whether it's degree, in degree, out degree, nearest neighbor degree, excess degree, etc. And we're going to consider the distribution of these values. Okay. And to study this in iGraph, there's a bunch of functions that exist. So degree just gives you a vector in which each vertex has its degree that is given. And again, as usual, in degree, out degree, or degree, depending on the case. And this is an option that you have to give to the function. The degree distribution is then going to give you a numeric vector that has the same size as the maximum degree plus 1. And what's going to be in there is that you're going to have the relative frequency of each degree in the each value of the degree. Okay, so it starts with 0 degree. How many are there vertices that have a 0 degree? There can be some, okay, they're not connected to anything else. So that's the 0 degree vertices. The second will be how many vertices have degree 1, how many vertices have degree 2, and so on and so forth. And that is going to be expressed in relative frequency, so that sum of everything will be 1. K&N is going to give you the average nearest neighbor degree. Okay, and it actually gives you two answers. One is the distribution, and another one is just the numbers. Okay. And I'll point out something that would have been helpful, for example, for some in Dijkstra. Very much like degree, well, I mean, so we've seen that in Dijkstra, but it happens a bit everywhere. So this, you can think of degree as applying to edges or arcs that have weight 1. So exactly the same way as in Dijkstra's algorithm, we computed things and said, okay, we'll take the geodesic distance, which is attributing a weight of 1 to each of the edges or arcs. Well, in the case of degrees, you can do the same, because you can, if you have a weight on the arcs or the degrees, the edges, then you can sum these weights instead of summing just how many there are. Okay? And this is going to give you a measure of, for example, potential for flow in the graph, etc. And now I'm really done with this lecture.